So I've got two wires running up there, so you can see them running from the top to the bottom. The current, the electrons are coming out, going up this side and coming down that side because the two are joined at the top. And I'm going to switch on a fairly heavy duty power supply that's able to provide more than 10 amps.
They're like repelling each other.
Yeah, they're just trying to push each other apart until they trip the power supply. What we can do as well is if we change the current, instead of the current going up, those two together, so the current's running straight up, take the current out from the top here and bring it well away over at the side here. See what happens in this case. Firstly, what do you think might happen? Now, what you might not be able to see is that what the class is doing is they're going like this, like that. Which is good, because it's to do with that, isn't it? What do you think might happen there? Kirsten, take a flying go. Yeah, let's see. Actually, Andrew, could you just hold that up to the side? I'll come back to why that's got to be held up without the way at the moment. But as we just switch the current going, so this at the moment here we've got current running parallel up between the two conductors. When I do that, they do tend to pull together there. So there's a force of attraction between the two. Force between conductors. And if you've got, better use a ruler, otherwise two guys are going to have a real go at me, I can tell. So if you've got two conductors where the current's going in opposite directions, what was the force that we observed there? Yep, okay, so they would tend to push apart with a mutual force there. If the two were running in the same direction, in that case the force was attractive. So that was what was observed. Now with the bigger the current, the bigger the force we get, but it's quite difficult to show that with this sort of equipment. Now, I asked you to think what the explanation was for that. Why are we getting that effect? First thing was that you've got, if you have a current going through a single conductor, what you found last time by putting a search coil here, the search coil was picking up the magnetic field that, because the current's going down, the motion of the thumb, the motion of the electrons is going that way, the fingers would be wrapping around, so the field was wrapping around in that direction, and you found that as you plotted against the radius away, that went down like that, and then you replotted it 1 over r. One over r gave you a straight line. What was the equation that sort of rolls all that together? Okay. So for a conductor, if it's carrying a current I, the current running through it there divided by the radius, multiplied by the constant, this time mu naught over 2 pi, not 4 pi. Mu naught over 2 pi is the magnetic field that you would get at that particular radius. Okay, so the field gets less and less as you go out over there. So one of these conductors here is going to be caused, if we forget about the second conductor for the moment, one of these is going to be making a field. This time it would be in that direction, because if your thumb's going up, the fingers wrap round like that there. So that means that at this point here, you've got a magnetic field that's effectively coming out of the board. So drawing it with that sort of arrow to convention, at this point you've got magnetic field out of the board at you. Yet we've put a wire into a magnetic field. The wire has got current traveling perpendicularly to a magnetic field. And that takes you back to the experiment that you just did last week, where if you've got a wire going through a magnetic field at right angles, motion of the electrons, your thumb, fingers as the field, in which direction would that wire be pushed? Palm is the push. Andrew? So that would be pushed down the way. And the force, what was the equation for force? Yes, ILB. So the force is equal to I times the length of the wire times B. So that's the field which is existing here because of this wire over here. So the reason that this experiences a force pushing it in that direction is that you've got a field coming out of the, so my fingers are coming out of the board. Yes, that's the way I drew it. Thanks, Ben. Phew. Thanks, Ben. Okay, so with that one going down like that, your fingers, the field is coming out of the board. Your motion of the electrons, the thumb, is that way, and you're getting a push out the way. What's the force actually going to be between the two? Could we come up with an equation that would give you the force? If we know what this current I1 is, we know what that current there I2 is, could we get an equation for the mutually repulsive force if they're separated by a distance r? We know what the field is, because that's the field at a distance r away from a conductor. We're taking this conductor here. We know that if we put another conductor in that field, then you experience that force. So how could you combine the two equations to give you the force between those two conductors? What would our equation F equals be? Yeah, so take whatever that B is there, put it in where that goes. So we've got that times that, and if we keep the constant out the front here, we've got mu naught I1 times I2 over 2 pi r. And we've got B in there as well. So if that's I1, that's I2, we're really just putting in, substituting that into there. We get mu naught I1, I2, B over 2 pi r. That's the force. Oh, there's one thing I've missed out there. Yeah, so we need L as well there. Now, this theoretically only works if you don't have any end effects, if at the end here it's not really turning a corner. So theoretically, these would be two infinitely long conductors, and in which case you cannot really talk about the length. But what we do instead is to say, right, it's not the actual force of two conductors that have a length. We just say that there's a force per unit length. So the force per unit length between two conductors is mu naught I1, I2 over 2 pi r B there. And that's the way that it's shown in your study guide. Okay. So the actual force is easy enough to get. You just combine the two equations. But it's really the number of newtons for every length of meter of infinitely long conductor. Admittedly, infinitely long conductors aren't easy to come by. But that's theoretically what you would have. One of the nice, it's a practical application of this idea is that this is actually where the definition of 1 amp of current comes from. 1 amp is defined as if you've got two conductors 1 meter apart which have a force of 2 times 10 to the power minus 7 newtons of all numbers. So 1 meter apart, they've got current running through, the same current of 1 amp running through, 1 amp through there, 1 amp through there. Those two conductors will experience a force of 2 times 10 to the minus 7 if they're a meter apart. That's where we actually get 1 ampere of current. And 1 ampere of current then determines what 1 coulomb of charge is. That's one of the fundamental sort of quantities of physics from this equation here. Okay, all the other units that you'll be using here are obviously amps. Units for magnetic field from last week, what was that? Tesla, yeah. So Tesla for field, the distance would have to be in meters. And your constant is your 4 pi times 10 to the power minus 7, all the other units for that. Okay. So we'll have a go with some of that now.